I will briefly have to apologize for our director, Martineau, who unfortunately cannot be present today. So I'll briefly introduce this program and the Solvay Institutes, upon which Frank will take over the floor. I will briefly so the International Solvay Institutes for Physics and Chemistry are mostly known for the 3-yearly Solvay conference in physics, which started in 1911, and the 3-yearly conferences in chemistry, which started in 1922, and which are going on till today. However, since the beginning of this century, 21st century, we expanded the range of activity considerably. So, for instance, we have now regular topical high-level workshops in the fields of physics, mathematics, chemistry, and life sciences, which not only bring together leading experts in the fields, but combine them with young graduate students in Belgium. We have every year the Jacques Solvay International Chair in Physics and the International Solvay Chair in Chemistry, where a leading expert teaches a series of master classes, mostly addressed to postdocs, grad students in our country. Then besides that, we have the regular Solvay colloquia, which addresses hot topics in the fields again, physics, mathematics, chemistry, and life sciences. And they are usually given by the leaders in the field. And the nice thing about it, that they are presented in such a way that it's accessible to a wide range of broad audience of scientists. Then we also have the doctoral school in theoretical physics, together with our partners in Paris, Geneva, Zurich, and Amsterdam. Then one of the things we are really proud of are our yearly public lectures, which are held in the magnificent Studio 4 in the Flagey building in Brussels, where top science is brought to a wide audience of interested people. I have to mention here that this year we will have 2 public lectures, as the one of last year was postponed because of the pandemic. So there will be one on 12th September and another one on 24th of October, and in slightly different formats. And then last but not least, since 2018, we have the New Horizon lectures in chemistry and also New Horizon lectures in physics, which are given by brilliant young scientists, which already achieved a high visibility and a well-established stature. So like I said, we started in 2018. Our first lecture then was Zohar Komarhovsky from the Simon Center. That was followed in 2019 by lectures by Alexandra Walczak on biophysics from École Normale in Paris. And then last year we had Douglas. Scheduled, but again, because of the pandemic, we postponed it till this year in the hope that we could have it in person, but well, we were too optimistic. So today we'll have them using the modern technology, which unfortunately we have become well acquainted to. And then I can already say that this year we will also have the 2021 New Horizons lecture, which will be given by Maria Bergerman from the Max Planck Institute in Heidelberg. So that will be astrophysics. And that will be in October, the month of October. And then finally, also the lecture for next year has already been determined. And this will be Nir Navon from Yale. So that will be more condensed matter oriented. So now I pass the floor to Frank, who will introduce today's and the next day's speaker.
Okay, so we are absolutely delighted to welcome Douglas Stanford for this series of lectures. This will be the high peak of actually a hard work that we have been starting a few months ago here in Brussels, studying topics that Douglas will overview. So Douglas did his PhD in Stanford under the supervision of Lenny Susskind. Then he moved to the Institute for Advanced Study in Princeton as a postdoc. And he is now an associate professor at Stanford University. He has, over a decade, made several seminal contributions, in particular to the fields or to the field of the quantum mechanical properties of black holes, and some salient features of his contributions include making the link between the so-called butterfly effect or chaotic properties at the quantum level and black holes. So Douglas, please, you can start, and we're all super happy to have these lectures.
Okay, yeah, thanks.
At least, at last, in spite of this horrible pandemic that, you know.
Yeah, well, thanks for having me. It's a pleasure to be here, and thanks for the flexibility surrounding the circumstances of these lectures. So I guess normally what this is I would be traveling to a few different institutions and getting to meet a lot of you in person and having kind of relaxed, informal seminars. I think it would be kind of a two-way thing. Like I would talk a little, you guys might tell me some of what you're working on, and it would be nice interaction. So I don't really know how to simulate that over this medium, but we can try to keep it informal. And please don't be shy about interrupting to ask questions or make comments or anything like that. So just please do participate as much as you can, and hopefully that will work best. So okay, let me get my screen going. So the topic of these lectures is going to be about space-time wormholes, and I understand that you guys have been reading a little bit. Well, some of you have done important work on this topic, so there's a fair amount of expertise here. So please do jump in. You can also suggest a different area if you're not too interested in exactly what we're talking about at the moment. We can try to be flexible. But the first lecture today, my plan is to introduce what a space-time wormhole is and why they're kind of confusing in their applications in theoretical physics. So that's what I'm referring to here as baggage. So here's some references, kind of early references on the topic of space-time wormholes. So there were three papers. Whoops. This is getting Strominger paper by Lavrelashvili, Rubakov, and Tinyakov, and one by Hawking. These papers were basically at the same time, and they were exploring different aspects of what we now call space-time wormholes, and they were all pretty confused, I would say. And then there was a paper shortly after that by Coleman, where he gave an interpretation of these wormholes that has more or less stood up since then. There was a new wrinkle in this development of this story with the introduction of thinking about space-time wormholes in the context of ADS-CFT. And so these papers here by Maldacen and Maus, Akarni, Hamed, Orger, and Polchinski were trying to understand, again, some of these weird conceptual puzzles in the context of ADS-CFT where things are a little bit sharper. So we'll talk about all these things and kind of follow up on some of these references today. Okay, so first of all, what is and what is not a space-time wormhole? I remember it was like 5 years ago or something like that I heard a seminar about this at the IAS, and I was confused about what space-time wormhole was and how it was different from an ordinary spatial wormhole like what you find in a black hole. So we'll try to discuss that. So here's a definition taken from the beginning of the paper by Akarni, Hamed, Orger, and Polchinski. They say a space-time wormhole is, or space-time wormholes in general, are extrema of the action in Euclidean signature of quantum gravity. So these are solutions to the equations of motion that connect together two asymptotic regions or arbitrarily separated points in the same geometry. So let me try to draw a picture of what we're talking about. One example would be, we have two asymptotic geometries, one over here, one over here. And there's some wormhole like this that connects them together. So you can imagine we have something that's like asymptotically R4 on the left, something that's asymptotically R4 on the right, and then a wormhole that's connecting them together. And it's called a space-time wormhole because if you think about the mouth of the wormhole, like roughly here and there in the two R4s, they're localized in space and time. So there's kind of a space-time point where the wormhole exists in both copies. It's not really a point because it has some finite size, but it's localized in both space and time. Okay, so that's one example. Here's another example. So that's an example of one where it's connecting two asymptotic regions, but we can also imagine that we have just one asymptotic region like this, and then we have something like this. Some wormhole that's connecting together 2 points. And this drawing is hard to make. There's something misleading about this drawing, which is that it looks, from this perspective, like the points that are connected together by the wormhole are kind of no closer through the wormhole than they are through the parent space. But that's just because we have trouble drawing these things. And in principle, the wormholes can link together points arbitrarily far away. So for example, one way to draw that is I can take the same geometry and fold it over like this. So I take the original R4 that we started with and fold it over like that. And then we can have the wormhole joining together these points here. So I don't know if this drawing was at all clear. Doesn't look super clear, but this is supposed to be joining together 2 points that are quite distant from each other in the background R4 or R2 in this case, but with a short wormhole. So that's kind of the deal. There are these geometries that connect together two asymptotic regions, like the one on the left, or that connect together very distant points in one asymptotic region, arbitrarily separated points in one asymptotic region. Okay, so that's the definition. Okay, so what isn't it? So here's the point that I got stuck on when I first heard about this, which is that yeah.
Maybe I have a question.
Okay, great.
So you introduced these Euclidean wormholes.
Yeah.
I think that, can you just tell us whether these Euclidean geometries typically have a continuation to real time or no? Is it useful to think about those guys, in terms really of space-time, or are they fundamentally Euclidean?
Well, it's definitely interesting to think about them in the context of space-time, and we'll do that a little later. And there's different ways that you can continue the same geometry to Lorentzian space-time. One way that we'll talk about in a second, which is important and interesting, is if I take this geometry here and I cut it across there, and then I try to continue that thing. So I consider this direction to be time. And let's say I cut the geometry in the dashed line, and then I continue it in the direction of the red arrow. Then this looks like a Lorentzian process where a baby universe is created. So if you think about the time slices at an early time here, we have just space is just a line, just an R1. And then at later times, we have a space that consists of a line and a circle. So a baby universe, the circle, gets created. So yeah, it's very interesting to think about these geometries in Lorentzian signature. But the starting point here is in Euclidean signature, and then you think about continuing them.
Okay, thanks.
Yeah, I just wanted to say a little bit how this is different from the spatial geometry of an Einstein-Rosen bridge. The Einstein-Rosen bridge of a black hole, sometimes we picture it like this. Some wormhole like that. And the point I want to make is that this, in the context of a black hole, this Einstein-Rosen bridge is a spatial wormhole. So the time direction is not drawn here. And if you follow this thing for time, you find that in Lorentzian time, you find that the wormhole kind of crunches. And if you follow it in Euclidean time, something more interesting happens, which is that you find that the two ends of the wormhole get connected together. So they're not really in different asymptotic regions. But this is a spatial wormhole, which is like a wormhole that exists for different times. Whereas a space-time wormhole is one that where the drawing is all of the space-time coordinates. So just to be completely clear, I've drawn here something which looks like a something that looks, it's a two-dimensional surface, two-dimensional wormhole. So this could be a spatial wormhole in a 2+1 dimensional theory, or it could be a space-time wormhole in a 1+1 dimensional theory. So a two-dimensional Euclidean theory, or a three-dimensional, it's a space-time wormhole in a two-dimensional theory, or a spatial wormhole in a three-dimensional theory. So that's the difference between space-time wormholes and spatial wormholes. And their interpretation in is a lot more confusing. Spatial wormholes we kind of understand. They represent something like entanglement of quantum states. That's the concept that we think underlies spatial wormholes. Space-time wormholes, it's less clear, and we'll discuss that today. Okay. So if you want to have in mind a metric to think about, the one I'm going to draw here is actually not a classical solution, so it technically does not satisfy the requirements of the definition, but it's just a really interesting metric, and this is from the paper that Hawking wrote. He gave this as an example of a space-time wormhole, and he said, even though it's not quite a solution, it's an interesting geometry. And it looks like this. Just this. So if we look at this metric, and we look as x becomes large, then we can ignore that term, and we just get flat space. If we look at x small, it looks like we have some kind of a singularity. But by redefining coordinates like y, we define a coordinate y that's like x over x squared. Then we find the same metric again. So the region x goes to 0 is really y goes to infinity. What that means is that there's another asymptotic region, another flat asymptotic region at x goes to 0 in this geometry. So this geometry here really looks like this one here. You have a infinite flat region at x goes to infinity. And you have an infinite flat region as x goes to 0. And they're connected together by something which has size. This size is roughly b. So it's this parameter here, b. So that's an example of a very simple metric that has these two asymptotic regions and a connection between them. So this was discussed in the paper Hawking wrote. He pointed out it's not a solution. It's not a vacuum solution of general relativity, but it's still kind of an interesting metric to think about. Okay. So first question you would like to ask is, do such solutions exist? Are there solutions to general relativity that have these space-time wormholes? And well, they do. They're kind of tricky to find. They're not as robust as other kinds of solutions, but they do exist. And we'll discuss that a little later. Another question you could ask is, should we even care if they're classical solutions? Like if I find some nice metric like this one that we just wrote, who's to stop me from including that in the gravitational path integral? And maybe the qualitative effects of that geometry don't depend on it being a classical solution. Maybe we can still think about the effects of these wormholes even if we don't write down classical solutions. So both of these questions are things that we will come to later. And we'll discuss some of the ways that you can construct these wormholes and cases where you don't even have a classical solution, but you still can include them. So we'll discuss those points later. For now, what I want to do is to just assume these wormholes exist. Assume that either we have solutions or we have almost solutions that we're going to include anyhow, and just discuss some puzzles associated to them. That's what this baggage is supposed to refer to. So why are these things confusing to interpret in general relativity? And that's what we'll do now. Okay, any questions on the definition or motivation before we get started on these puzzles?
So let me emphasize people should not be shy asking simple questions. Okay, as Douglas said, it should be kind of informal.
Yeah, the simpler the better, honestly, because it's kind of early in the morning for me. And if you ask me a really complicated question, I don't know, I don't know what'll happen. But okay, well, don't be afraid to jump in anyhow. So let's see. Okay, so here's the first puzzle, and this was the one that the people who wrote these first papers, getting Strominger, Lavrashvili, Tinyakov, Rubakov, and Hawking, this is the puzzle that they were mainly worried about. And it has to do with exactly what Frank was talking about earlier, taking a Lorentzian continuation of this geometry, one of the wormhole geometries that we drew here. This one, taking this guy here and then cutting it along the red dashed line, taking half, okay? If you just think about what that looks like, I've just redrawn that a little bit better here. And the papers were thinking about this as a kind of instanton or some kind of tunneling event where you create another universe. So if we think about this dashed line here as the space, and we think about time going upwards, then as time advances, we go from a spatial topology that looks like just a line like this to a later time where a time slice intersects both parts, and we have a line and a circle. So the circle represents the spatial geometry of a closed universe. So this geometry, when we think about it this way, when we cut it open like this, it somehow represents a creation process of a closed universe. We go from one infinite line of space to an infinite line of space plus a circle. The circle is called a baby universe. So that's this thing or that thing. Okay, so that's what the interpretation of this space-time is. Now, let me clean this up a bit. The papers I mentioned were worried about this because they said that it leads to a phenomenon they called loss of coherence. And what loss of coherence means basically is that a pure state of the universe ends up as a mixed state. So let's see if we can understand why that would happen. Let's imagine that we have two entangled particles before the baby universe is formed. So the red line connected together is supposed to represent two particles. The connection is their entanglement. And then let's imagine that one of them falls into the baby universe, and one of them stays outside. Then at late times, after the baby universe is created, we just have in the main part of the universe, in the non-compact part of the universe, we just have one of these two particles. The other one is stuck inside this closed universe, and it's inaccessible. It's not connected in any way, in any spatial way, to the observer's universe. So let's say the observer is over here. So that observer looks at this situation, and they just see one of these entangled pair of particles. And they conclude that the universe is in a mixed state because that particle is entangled with something inaccessible. So we have a pure state initially at early times, with these two particles entangled with each other. One of them falls into the baby universe. The other one remains, and it leads to a mixed state. So this is, I don't know if this reminds you of anything. It's basically the same problem that is the black hole information paradox that you can have in a black hole setting. The problem is here, I'm going to have to make the analogy, I have to draw the black hole backwards. That's going to be challenging. Let me see if I can do that. So here's a space-time drawing of an evaporating black hole, the Penrose diagram. And the Hawking radiation process is basically this. You have an entangled pair of particles created at the horizon. one falls into the black hole and the other comes out. And that's very much parallel to what we're discussing on the left here. And the black hole information paradox is basically the statement that if we look at some late time slice out here, that we just have one of those particles. So it appears to be in a mixed state. So there's a close connection between the loss of coherence problem associated to these wormholes and the loss of coherence problem associated to the evaporating black hole.
So Douglas, is it important that you have observers like everywhere on a slice on spatial slice? Because otherwise, if you were in de Sitter space and you were restricting to a single observer, they could also find themselves with one of the particles and the other one could not be accessible anymore to them.
Yeah, so let's see. So let's draw a de Sitter space. So you have in mind some observer in de Sitter space traveling on some trajectory like this. And you say we could take a pair of particles like this, or one falls out of their de Sitter patch and the other one remains in. Is this roughly the setup that you have in mind?
Yes, right.
Yeah, so in this case, you're right. The observer would conclude that the system is in a mixed state. And as far as I know, there's no real problem with that in de Sitter space. Somehow, I guess the static patch of de Sitter space where that blue observer lives, well, people don't know how to think about de Sitter space in quantum mechanics, but at least it's one seemingly viable idea to think that that system is described by a mixed state. Due to precisely this kind of phenomenon, due to this, but that might be wrong. Maybe there's some more exact way of thinking about it, where it's not exactly, you're not really a mixed state, it's just a complicated pure state. I'm not sure.
But so in the case of the wormhole, isn't that sort of similar? I would have said that the puzzle would be if the baby universe disappears or evaporates somehow. But if it's still there, for all time, okay, you don't have access to it, but you could still set up some quantum mechanical theory that takes into account this baby universe, no? So if it doesn't go away.
Right, so if it doesn't go away, then you say, it's okay, yeah, the universe is now in a mixed state because the purification is this baby universe. And that makes sense to us because we know where the purification is. It's not accessible. It's in this other space. It's sort of, yeah, it's, as you say, sort of like de Sitter space. You say it's fine to have a mixed state here because there's some other system that we're entangled with. And that happens all the time. In quantum mechanics, what's the big fuss? And yeah, that could make sense for the baby. Well, whether that could make sense or not, it's at least a good thing to think about especially for the baby universe. It leads to problems, though, that, well, you could say, and some people do say the same thing for the black hole. They say, yeah, the black hole, the Hawking radiation ends up in a mixed state because the partners fell behind the horizon. And we know where they are, they're over here. And you can think about the region behind the horizon of the black hole as like a baby universe. And the black hole formation and evaporation process as being the creation of a baby universe. So they say Hawking radiation really does lead to a mixed state, and the purification is contained in the baby universe, which detaches from the rest of the universe at the final point of evaporation. Now, abstractly, that's possible. It runs into some difficulties when you think about the fact that it means that you have to be able to store a lot of states in these very tiny evaporated black holes or disconnected evaporating black holes. But in principle, it's something that one could take seriously. I think it's not right. It's not the right interpretation either of the black hole or the baby universe, and we'll discuss why that's not right. But it's not like it is immediately a contradiction. So it was something that these authors were worried about, but they didn't say, okay, that means that theoretical physics is doomed. Like Hawking in his paper said, yeah, this looks a lot like the evaporating black hole, and I think that that also leads to a mixed state. So coherence is lost. You get entangled with baby universes. So I'm not trying to imply that just from this picture, it means that there's a logical contradiction. It's just a little bit funny. It's something that we'd be unfamiliar with.
So I have another question related to your the space-time wormholes you've drawn. Maybe it's related. So imagine you try to do a description of gravity in the Hamiltonian formalism, okay, like canonical gravity. Can you do that and still describe this sort of solution? So in other words, you know, like within the usual Hamiltonian quantum gravity, can you imagine a process where your spatial slices change the topology like this?
Well, I think you can imagine it. You just have to use a Hilbert space that includes baby universes. So you'd have to work in a Hilbert
at the classical level. Well,
this is a quantum effect. So this is like a tunneling effect that would take you from one subspace of the Hilbert space with no baby universes to another subspace that has baby universes.
Okay, so you say it can be a solution of the Euclidean Einstein equation, but never of the real-time Einstein equation, or is it?
Yeah. Like if you try to have these just in pure Lorentzian signature, there would have to be some singularity. Yeah. So it really should be interpreted as some kind of a tunneling process. And
I see. Okay, so you would have to set up some canonical formalism, as you said, where it's like some sort of third quantized version where you have all these baby universes that you can create and etc.
Yeah.
If you don't do that, you sort of remove all this discussion from scratch.
Yes, but then it feels like your formalism is not good enough to account for everything that gravity can do. So it seems like
probably
the fact that you can have geometries like this that can, when cut open, represent this tunneling process means that you need to include the end point of the tunneling process in your Hilbert space. Like if we're just talking about a particle stuck in like in quantum mechanics, if we were talking about some problem like this, and we just lived here and we just described a Hilbert space that described the particle living in this false vacuum, we would be puzzled by these Euclidean solutions that allow us to tunnel out, and we would have an inconsistent theory if we didn't enlarge our Hilbert space to describe the endpoint of that tunneling. So I think it's probably the same here in gravity, that these Euclidean configurations mean that you really need to describe, need to include baby universes in the Hilbert space.
Thanks.
Okay, so for this puzzle, I want to try to give a type of resolution of this puzzle now. The other two puzzles we'll discuss in a second, we won't have such quick resolutions for. But this one is really interesting, and it's basically the same. I think it's basically the same resolution as for the replica wormholes that explain the page curve for evaporating black holes. So I think if we somehow thought harder about this puzzle that was discussed in these wormhole papers, we might have figured out the replica wormholes a little sooner. So here's what I want to discuss. Is coherence really lost in this sense? So here's what we're going to do. We're going to compute the density matrix of the universe after the baby universe is formed. And we're going to just check, is it in a pure state? So to check if it's in a pure state, we're to compute two things: trace of rho squared and trace of rho squared. And if those two things are equal, then it means that the state is pure. The rho is a multiple of a projector on a rank 1 projector. So if we can show that trace of rho squared is equal to trace of rho squared, then that means that rho represents a pure state. The density matrix represents a pure state, and coherence was not lost. This is basically the same thing that one does in the replicable wormhole analysis of evaporating black holes. So, so let's try to do that. Okay, so here's a drawing. I don't know if this is going to be confusing or not, but this is supposed to be a drawing of the density matrix after the baby universe is formed. So the density matrix that's accessible to our observer here, who has access to the entire universe, the entire non-compact part of the universe, the whole everything but the baby universe. So they describe a density matrix, which is like it looks like this. It's like a ket bra, where this is the ket and this is the bra. And the boundary conditions that they would put would be something like, okay, I know that a baby universe just formed, so we should draw a space-time where a little while in the past, there's some kind of an opening and a baby universe was formed at that point. So they do that both in the ket and in the bra. That's the boundary conditions for that gravity problem. They put whatever state they want up here, the red squiggly line, and then in a little bit in the past, they require that a baby universe should have formed in a tunneling process. So this is like a gravitational description of the boundary conditions, the definition of the problem for computing the density matrix after the baby is born. Okay, so let me clean this up and okay, let's try to do this. So now we want to compute trace of rho. And to compute trace of rho, what we do is we take the bra and move it around and sandwich it with the ket and sum over the states that formed there. So we find a geometry like this, and it has two of these baby universes to be, and we can fill this boundary condition in with a gravitational computation where we just link those together like this. So we have a wormhole geometry, and summing over the red boundary conditions removes these things. So the whole computation of trace rho is just the gravity path integral on this wormhole geometry. So that's trace rho. Okay, now let's compute trace rho all squared. So we just do two copies of the same exact calculation, and we come to the same conclusion. We connect these things together. We delete this state that we're summing over, and we just have two copies like this. But now you'll notice that there's another possibility, which is that we could connect this wormhole here and this wormhole here. So this is a very strange situation where we find that trace of rho and trace of rho squared are kind of different gravitational computations. In particular, trace of rho all squared has more contributions to it than you would have thought from just taking two copies of trace of rho. We can also have this contribution where the wormholes cross each other. Okay, but our interest is not to compare trace of rho with trace of rho squared. Our interest is to compare trace of rho squared with trace of rho squared. I'm trying to differentiate between these with microscopic pauses in the speech. It doesn't really work, but I think you guys have, you know the two things we're computing. We're computing this thing and this thing. So far, we've just computed the one on the left.
So, sorry, Douglas, no, I'm confused even with the statement that trace of rho squared is trace of rho times trace of rho, something I'm trying to teach my 5 years old, you know. So is it?
Right, so here somehow it's not true. It's not true. Okay, let me try to be more precise about what it is and isn't true. So here I tried to break up the computation into two steps. Step one is you write down the boundary conditions And then step 2 is you evaluate in gravity. So, for example, we can see the boundary conditions for, I've kind of, let me try to do that better. So let's go back to this example. Yeah, thank you for the question. Okay, so this step here, I would say corresponds to evaluating the boundary conditions for trace of rho, but we haven't evaluated the answer yet in gravity. We evaluate the answer when we fill this in, when we find a solution that fills in those boundary conditions. So we have boundary conditions which say, baby universe forms here, baby universe forms there, I don't know what the wormhole is doing. And to evaluate in gravity, you connect those things together with a wormhole. So we can think about this, if we think about it, let's use some notation where G of whatever corresponds to evaluation in gravity. Okay, so what we computed here was G of trace rho. So we set up the boundary conditions for trace rho, and then we actually evaluated by linking those things together with a wormhole. We computed the gravitational evaluation of that G of trace rho. Okay. What did we compute here? We computed G of trace rho squared. Sorry, that's equal to this plus uncrossed. So G of trace rho squared contains two contributions, the crossed wormhole and the uncrossed wormhole. Okay, so now you're asking about consistency with elementary school multiplication. And that is the following statement, that this is not equal to G of trace rho squared. So G of trace rho was the thing on above, and G of trace rho squared is not equal to it. Sorry, I said something stupid, but these two things are not equal to each other. And hopefully I've explained them in a way that you can see that that's possible.
Okay. So already there, you have some puzzles with quantum mechanical interpretation.
Yes, already here we have some puzzles.
Beyond this.
Yeah. What does G correspond to? Yeah, exactly. Here we have some puzzle. But what I'm claiming is that the puzzle is not that the universe is in a mixed state. Okay. That's not the puzzle. There's some other puzzle.
That we will talk about maybe later.
We'll talk about that in the next step. Yeah, later. There's some puzzle. And well, this was really Coleman's point. This is not something novel I'm saying now. It's that the puzzle is not that the universe ends up in a mixed state. There's some other puzzle. So this thing that folks were worried about, loss of coherence, this isn't what's going on here. There's something else going on which we'll try to understand.
So Douglas, so you're distinguishing clearly between, let's say, the big universe and then the baby universe. So why are you treating the two future regions, say, differently? I guess it has to do with what is boundary and what is fluctuating, or
yeah,
I mean, a sharp distinction.
We could try to make this a sharp distinction by imagining a process where we let all the stuff there, like, go out, sort of move out to asymptotic infinity so that gravity turns off. So after the baby is formed, we wait a long time, all the stuff that's here goes out to asymptotic infinity, gravity turns off, and we can make sense of the computation of rho and trace rho squared. And in that sort of asymptotic final state, you just have the stuff in the main part of the universe and not the baby. So the question is whether the stuff in the main part of the universe at late times ends up in a pure state or not. And by looking at this diagram, you would say, obviously, no, it does not end up in a pure state because it's entangled with the baby and you're not including the baby. But my claim, and Coleman's claim, is that it actually does end up in a pure state. Okay. Does that answer your question? Sorry.
Yeah, I'm keeping this de Sitter analog in the back of my mind, and I try to figure out what's going to be different if I try to apply the same logic to that.
Yeah, it's a good question. I'm not sure. So you want to say, take de Sitter space and just try to compute the entropy here. You know, it's actually possible that in that case you also conclude that you get a pure state. I'm not sure. I'm not sure. It's a really interesting question. I'm not as convinced that the computation makes sense in de Sitter space though, because we can't let things kind of move apart into some non-gravitating region where we can definitely make sense of the quantum mechanics of the final state. That sounds like a poor excuse though for what is definitely an interesting question. So yeah, thanks for raising it, but I don't have a good answer to that.
Okay, thanks.
Okay, but let me just continue along here. Wait, let me see. There's a question. Where's the observer in the universe or in the baby universe? Yeah, the observer, let's say, is in the main universe. So the observer is some like particle detectors at asymptotic infinity after the baby universe is created. You wait a long time and then collect the quantum state in the main part of the universe. Okay, so let me try to clean this up and continue with this discussion. So far we computed trace rho and we computed this thing here, trace of rho all squared. But now we want to compute trace of rho squared. So let's build, first we'll build rho squared and then we'll compute its trace. Okay, so to compute rho squared, we take two of these things and multiply them together. So it looks like this. So this is rho squared. And to compute trace of rho squared, we just bend the bra around and sandwich it with the ket. So let me erase this drawing to make it a little more space. What that looks like is we take this thing here and we move it up there. Okay. So we end up with this. These are the boundary conditions for trace of rho squared. And now what we're going to do is we're going to evaluate G of trace of rho squared. And you can see that the boundary conditions that we have, I don't know if you remember at this point, but they are exactly the same as the boundary conditions that we had for trace of rho squared. That's because here's a boundary condition for trace of rho. And we just take this thing, we take two copies of this to write the boundary conditions for trace of rho squared. And the boundary conditions there are exactly the same as what we have below for trace of rho squared. We just have two copies of this kind of cut open wormhole.
So sorry, Douglas, why when you compute rho squared, you didn't connect the two baby universes?
Right, so the rho is referring just to the quantum state of the universe itself. So it's the quantum state of the universe conditioned on some prior event that a baby was created.
Right.
And we don't say where the wormhole attached to the baby goes. So that's some boundary condition, which has some open ends, which is where the baby goes, where the wormholes, how they link up. And that kind of boundary condition is exactly the same as two copies of trace rho. So here you can see that we'll have the same situation. We can either connect these together like that, or we can have a configuration where we connect one with the other. So we'll have exactly the same result for trace of rho squared. So we're going to find that this is equal to G of trace of rho squared. Okay, so we conclude that the universe remains in a pure state. There's something else that's funny that's going on, but we conclude that the universe remains in a pure state. Okay, this explanation was probably confusing. We'll probably come back to it when we discuss the replica wormholes for an evaporating black hole. But I wanted to show it to you here, partly to, so we get to explain it twice, we get to discuss it twice in slightly different contexts, and also because, well, because it's an interesting way of thinking about this puzzle.
Sorry, Douglas, could you just repeat what happened? So you had the computation where the two things were different. Now you did something different to make them the same. What was the difference again?
Yeah, so from this argument, we concluded two things. This was conclusion 2 was this, and conclusion 1 was this. It was that G of it was that. So I think of the G function as saying, what is the answer for this question in gravity? So capital G stands for gravity. It's like gravity is telling you the answer to this question. So you can ask it various questions. You ask it, what is the value of trace of rho? And then you evaluate G of trace of rho. Okay, that's some number. And we find that the square of that number is not equal to the gravity evaluation of the square of trace of rho. So that's a puzzle. However, when we ask gravity, is the state pure? The way that you do that is that you evaluate G, two different things, trace of rho squared and the square of trace of rho. And gravity says, yep, those two are equal. So our conclusion is, I don't know what's going on up here, but the state is pure. Okay, and Coleman's interpretation of the question marks of what's going on up there is that gravity is really secretly describing an ensemble average of bulk theories, an average over couplings, and that the G function corresponds to an average over these couplings. So we'll describe that again in a second. Okay, any more questions about this first puzzle? I think it was a little bit confusing, but it's really important. Okay, well, let's continue on with the second puzzle. So this is one that those folks before were also aware of. But it was something that was particularly discussed by Coleman and that came back later in the ADS CFT context. So what is this puzzle? Let's say that we have an ordinary quantum field theory, and we compute some two-point function. Then a theory satisfying cluster decomposition has the following property, that this thing, in the limit that the points are very far from each other, becomes equal to a product. So it says that correlation functions of very, very distantly separated operators factorize. And that property is referred to as a cluster decomposition property. And what Coleman pointed out, or what some of the other authors also pointed out, is that these wormholes seem to violate the cluster decomposition property. And in fact, they seem to imply some non-local correlations. So in fact, a non-local term in the action, which is worse than just non-local correlations. Non-local term in the action of the effective description. So let's try to understand why. Here, let's go back to this other diagram. So where we have a wormhole like this, which is connecting to, could be very distant points, X and Y, in our parent space. So those points X and Y can be arbitrarily far apart, and they can still be connected by a relatively short wormhole, short Euclidean wormhole. And that will lead to a non-zero correlation between those points, because we can have like correlation of the O operators. The O operators don't think they're so far apart through this wormhole. So that leads to a non-decay of these correlations. Now, that sounds a little bit unusual, but it's not a flat-out contradiction with anything yet. But it starts to look worse if you try to represent this effect in an effective description. We can try to write an effective description that describes just the propagation of matter fields on the rest of the space-time, where we kind of get rid of the wormholes and represent them by some effective term in the low energy action. So let's imagine that we have some kind of a scalar field here. So we're writing some action for a scalar field. We can have the usual terms like d phi squared plus m squared, phi squared. We can have the usual terms for the scalar field. And then we want to ask, what are we supposed to add to this to include the effects of this wormhole? And well, you can kind of see what you're supposed to do, because what the wormhole can do is it can annihilate the field at location X and create it at Y. The particle can go into the wormhole at X, and then it can come out of the wormhole at Y. So we should add some kind of a term, which is like 5x, 5y. And because the wormhole can connect arbitrary points in space, we should integrate these over X and over Y. So now we have just a flat out, explicitly non-local term in the action. It's a bilocal term, but X and Y can be arbitrarily distant and separated from each other. So this gives us a non-local term in our low energy effective theory. Okay, so this is supposed to be a consequence of wormholes, non-locality of the effective theory, and a violation of cluster decomposition. Okay, but so Coleman gave a really interesting interpretation of this, which is connected to the puzzle that we just discussed a second ago. And the way that looks is the following. So we have this term in the integral over phi. So path integral over phi. We want to do something like this. So we're going to have a term. So e to the minus phi is equal to e to the minus I naught without the wormholes times e to the, let's say, integral 5x, 5y, dx dy. Okay, but what you can do is you can represent that as an integral d alpha e to the minus alpha squared plus alpha integral 5x dx. I'm not being careful with constants. But we can take this non-local term involving 5x, 5y, and we can rewrite it by doing an integral over some parameter alpha as a local interaction. So just a local term, just integral of 5x dx. When we do the integral over alpha, this Gaussian integral, we end up squaring this term here. And that gives us the expression written on the previous line. So the interpretation of this looks non-local. And this is the effective description, implementation of the wormhole. What is this? This is another way of writing the other thing. It's just a mathematical identity. And what it looks like is an average of local theories. with couplings alpha. So in this case, there's just one coupling, but in general, you can have more couplings for all the different operators that are represented by opening a wormhole mouth. So the non-locality that we found is really supposed to be an indication that we're doing an average over some couplings in the low energy theory. So we can trade the wormholes and their seeming non-locality for an average over some couplings. And now if we go back to the previous step, we can think.
I have just a small question here. So it looks like this interpretation requires that you're dealing always with annealed averaging, not quenched averaging. Right? So from my knowledge of statistical physics, like people usually say what is physical. So if you go to disordered systems, in the theory of disordered systems, what is physical is usually the quenched averaging.
I'm dyslexic with annealed and quenched. Which is the one where you do the averaging all the way at the end?
So I think what you have here is annealed because you do it on the partition function, whereas the quenched would be averaging the free energies, if you like. So the log of these integrals.
Ah, yeah.
Because physically, that's what usually happens is that you have a disordered system. You want to average over the physical quantities, which are these free energies, for example.
Yeah, this corresponds to an average where the averaging happens at the very end of the computation. So it's like it's the relevant averaging if our universe, if there really were some unknown couplings in our universe and we were averaging over our ignorance of those couplings.
Yes.
So then if we tried to compute trace of rho in that theory or whatever, we should average at the end. So the claim is that this G operation that we defined earlier gets interpreted now as average over couplings alpha. So if we go back to the previous discussion where we were evaluating things in gravity and we found puzzling answers, like we found this puzzle here. Well, that's not impossible if G corresponds to an average over some parameters alpha. So whether you average trace rho or trace rho squared, you could get a different answer.
Right. But also it's important that you average the way you did it. You could also define the averaging by saying, I will average over all the effective actions, for example. And that would not be the same because the effective action is like the logarithm of your path integrals, roughly speaking. And averaging over the log of the path integrals is not the same as the log of the average of the path integrals.
Yeah, that's right. That's right. That's right. So it's like we're averaging the path integral itself over these parameters.
Now that's sort of important, I think, but from the point of view of disordered systems, that's not the natural thing to do. So they always do the quenched averaging in some very simple examples like SYK at leading order, the two coincides, but that's very specific to this very simple model. In general, you need to do the quenched averaging. And that's what yields eventually to replica symmetry breaking for spin glasses, etc. So it's important for them, for people doing disordered systems. So here, it's.
So I guess
I had not realized. I'm putting out this because I had not realized that it's very important. It seems it's very important that we have here annealed averaging, which is you average the path integrals, not the logs of the path integrals, not the free energies, not the effective actions.
Yeah, I mean, if you want to, you can compute the average of the log of the path integral. Like you can compute whatever you want. So like we could compute. Whoops. In principle, we could compute G of log Z.
Right.
We would just have to set that computation up, and that would not be equal to log of G of Z.
You're right.
So the claim is that the averaging happens at whatever step you say, okay, now I'll evaluate this in gravity.
Okay. Right.
So you set up, define whatever observable you want to compute, and then you then the averaging happens when you actually compute it in gravity.
Okay.
Yeah, so we could compute averages of log z or logs of averages of z, but those will correspond to different.
Then there would be a big question, if you start to set up calculations like that, averaging logs, is it possible that we find something like replica symmetry breaking, the phenomena that you have in spin glasses within this gravitational framework? Replicas here would be useful because to compute the average of log z, you would compute the average of z to some integer power and etc. So there's also a replica trick, which is not the one we will talk about later, but here you also have a replica trick if you want to compute g of log z. That would be how you set up the calculation.
It's actually, yes, that happens. So a good example of that is when we're trying to compute, an interesting thing is to compute trace of rho log rho. This is the von Neumann entropy. And we think about this using a replica trick, starting with trace rho to the n. And actually, in this case, you can have replica symmetry breaking, depending on exactly which computation you're doing. So yeah, that actually does happen.
Okay.
That does happen in the replica wormhole calculation at some points during the page curve, near the transition that happens. So those effects here, I'm getting ahead of myself a little bit, but the page curve is some curve like this. And near this point, you have that kind of effect.
Okay.
I think it's not as, it doesn't have the same depth and complexity as like the Parisi kind of replica symmetry breaking, but it is.
Well, the Parisi story would apply to computation of g of log z. That would be the analog. So I don't think people looked into that, as far as I know. Maybe you can know more.
Yeah, there is actually a paper where people compute that. There's a couple of papers. I think there's one by Engelhardt, Fischetti, and Maloney. And then there's a recent paper, Merbabai and sorry, I've forgotten the other two authors of that paper, but okay. Yeah, they do compute it and they find some replica symmetry breaking also, but it's the kind of replica symmetry breaking that happens there. Let me just try to draw a picture of the kind of thing that you get. You have some kind of gravitational problem defined by some boundary conditions like these circles. And so replica symmetric configuration could be either you fill these circles in with disks like that. I'm just drawing a cartoon of some calculation to illustrate the replica symmetry breaking that happens. So you could have these replicated disks where you fill them in like that. Or another replica symmetric thing would be to completely connect them together like this. This also has a replica symmetry. But depending on exactly where you are in the parameter space, you might end up having to sum over things like this. And in some cases, you can do that sum exactly. And in cases where you can do that exactly, one case is this computation of the page curve. And you find that the effect of these things is to smooth out the transition in a particular way. But, well, that's just to say that like this can happen. It's not as interesting and kind of this amazing hierarchical structure in the Parisi analysis. I don't think there's anything that's been discussed that has that level of complexity and interest, but replica symmetry breaking in this sense does happen. Okay. Okay, so I think we're supposed to take a break at some point. Maybe now is a good time to do that.
If you think it's a good moment, we can do it now. It makes sense.
Yeah, let's do that now, and then we'll come back to the factorization problem in the next part.
All right. So we have our break. It's usually 5 minutes, but maybe, it will be 6 or 7, but not more. So try to be back in 5 minutes from now.
Okay. Okay, I'll see you guys in a few minutes then.
Alex, tu es là? Tu m'entends?
Attends, je suis
Moi, je
là,
suis
oui.
là.
Mais
Oui.
je pensais que ça durait qu'1 heure, en fait. C'est 2 heures le séminaire?
Oui,
Ah, ok.
oui, oui. Ça sera toujours 2 heures, les 3 fois.
Ah, zut. Ok. Bon.
Désolé.
Non, bah, j'avais pas prévu. Je croyais que c'était 1 heure.
Désolé. Ouais, c'est 3 fois 2 heures.
Ok.
Ouais.
Bon.
Bon, courage. Ça va? Tu peux rester?
J'avais cours, en fait. Je
Oui,
pense.
c'est ça.
C'est pour. Je pourrais partir et peut-être. Ça te dérange, Franck, si je te mets comme host et qu'à
Alors,
la fin,
ça ne me dérange pas dans l'absolu. Le problème, c'est que j'ai jamais utilisé la fonction enregistrement. Peut-être que Ben pourrait le faire mieux que moi parce que je sais qu'il le fait à chaque fois.
Ok.
Il faut peut-être demander à Ben quand il sera de retour.
Parce que moi, c'est un peu bête. Du coup, je reste juste pour arrêter l'enregistrement sur YouTube.
C'est ça.
Du coup,
Alors, comme je ne l'ai
vais
jamais
demander.
fait, j'ai peur de faire une boulette, quoi.
Non, non, il n'y a pas de souci. Alex?
Oui, moi j'ai aucune idée comment on fait ça avec YouTube. Je suis comme Franck.
Mince, ça doit sûrement être simple, mais il aurait fallu qu'on
Ouais, bah ouais, bon.
qu'on fasse le test avant et qu'on soit. Ouais. Peut-être que Ben demande à Ben parce qu'il est plus au fait.
Probablement, il prend une pause, il est probablement
Oui.
pas.
Non, là, il ne nous entend pas, mais il va revenir, on peut lui
Ouais.
demander. Ok. Bon, je passe aux toilettes, je reviens.
Hi, Ben.
Hey, Isabel.
Hi, how you doing?
Good, good. You?
Listen, yeah, I'm good. Listen, I was wondering if you could do me a favor, but you can say no. I didn't realize the talk was for 2 hours and I have to go to a class. I was wondering if I could make you host and just ask you to stop the live streaming at the end.
Yeah, so does that mean I just have to click on something to stop it?
Yeah,
or?
so if I make you host, you will see at the end of the screen more with 3 little points, little dots.
Yeah.
One of them says stop live streaming.
Okay, perfect. I'll do that.
Oh, fantastic. Thank you so much.
Thank you.
Okay. We'll do a test. I'll make you host first and you tell me if you can see those spots that tell you that. Make host.
I'll try not to stop it right away. Okay, I see the 3 dots. Okay, right.
And
I
you
will
see,
not click on it, but I can see it. It works.
fantastic. So it's really easy. You just need to click on that.
Okay, great.
Thank you so much.
Thanks, Isabel.
See you later. Bye-bye.
Bye.
Well, should we start again? I guess it's been what, 6 or 7 minutes.
Sounds good.
Okay. Are there any questions about this part? I'm not sure if it was clear, but this is this is super important. This is the main insight that Coleman contributed to this story, that you can think about the effect of these wormholes as describing an average over an ensemble of theories. So you can trade in the non-locality of the wormhole for an integral over these couplings. Okay, well then let's move to the third puzzle. So basically this third puzzle has to do with trying to interpret Coleman's idea in the context of ADS-CFT. Here are some references for that. Paper by Whitten and Yao, paper by Maldacen and Maus. This one we've been discussing by Arkani Hamed, Orgera, and Polchinski. So this is in the setting of ADS-CFT. And the simplest case to imagine is that we want to compute a partition function of the boundary theory. So let's imagine that the boundary theory is, so I can draw the pictures. So let's say D equals 0 plus 1 dimensions, boundary theory. So we want to compute a partition function, let's say Z of beta, where we place the boundary theory on a circle. And we compute Z of beta, where beta is the circumference of the circle. The circle represents the periodic Euclidean time direction. And the path interval in the circle just computes trace of e to the minus beta h. So this is the thermal partition function of the boundary theory. Okay, so the rules in ADS-CFT. Okay, sorry, I'm just going to call this Z from now on. I'm not going to call it Z of beta. So the way the ADS-CFT dictionary works is you write down the boundary conditions. So that's this circle out at infinity. And then you try to fill it in some way with some geometry. So for example, we can fill it in with a geometry that looks like this. And then calculate the gravitational action, fluctuations around that configuration, and that's the gravitational answer for Z. So this would be like G of Z. We're using the same notation where capital G means evaluate this thing in gravity, fill in these boundary conditions in gravity. And the content of the ADS-CFT correspondence is that this G of Z, the gravitational evaluation, is supposed to be equal to some direct boundary theory computation, some direct computation of this Z in the boundary theory. Okay, so what's the puzzle? The puzzle is the following. Let's first draw a diagram for G of Z squared. So that's this. So we have this, two copies of this same geometry. So G of Z squared is equal to this. And now let's draw diagrams for G of Z squared. So we can have the same thing. Let me just copy it. Okay, but what can we also have? We could have some kind of wormhole connecting the two. And this is not equal to G of Z squared. Okay, so this is what's called non-factorization. And this problem is known as the factorization problem associated to wormholes in ADS-CFT. Why is it a problem? It's a problem because the ADS-CFT correspondence states that this G of Z should be equal to boundary theory evaluation of the partition function Z in some particular boundary theory, like n equals 4 super-Yang-Mills with a particular value of the coupling. So there's some definite answer for Z from the boundary theory perspective, and the bulk computation is supposed to give that exact same answer, exact same numerical answer. Okay, and we can't compute that from the bulk theory. We can't do the exact computation in the bulk, so we can't check it exactly, except in some special cases. But we can see from this argument that in the first expression, G of Z squared, we're not going to have any contribution from wormholes. So that's this line here. We're not going to have any contribution from wormholes. And in the second line, we're going to have the possibility of a connection of the two asymptotic boundaries by a wormhole. And if that happens, it looks like we're going to be led to the conclusion that that is different from G of Z squared. And that would just be a flat contradiction with the idea that G of Z is numerically equal to the evaluation of Z in some fixed boundary theory. Okay, so that's the puzzle. And so these authors were looking at this puzzle from different directions. So Witten and Yao showed that in some circumstances you can't have a wormhole solution connecting the two sides. Aldecena and Maus, Arkani-Hamed, Orger, and Polchinski were working out some other cases where wormhole solutions do exist, and they were puzzled. They weren't sure what to conclude about how this is resolved, how this can be compatible with ADS-CFT. Basically, the conclusion that you want to have, according to Coleman, you want to use Coleman's idea and say that these things are not equal to each other because G represents some kind of ensemble average over theories. In this case, it would be an ensemble average over boundary theories. But
so Douglas, could you tell us a bit more about this sort of counter examples to Witten Yao? Because I thought in Witten Yao, if I remember, the starting point is extremely general, right? I mean, they don't really impose any bizarre condition. If I remember, there's some stability condition with the Yamabe invariant or something, but which is something that must always be satisfied.
Well, for example, they say that the boundary is positive curvature, and it's vacuum gravity with positive curvature boundary. And basically, right, if you have other fields and you have sources for those fields, or if you have negative curvature on the boundary, then you can evade this.
But wasn't the argument something like if you had negative curvature on the boundary, then the theory will always be unstable or something like this?
Well, yeah, it can be unstable to brain tunneling, brain nucleation. And there are some special examples where you can avoid this instability, but well, maybe it's better to talk. We're not going to talk about the negatively curved cases for that reason. Maybe it's easier to just think about the cases where you have a positive curvature on the boundary, but some sources turned on.
Okay.
And then the theorem doesn't apply because they were discussing just vacuum, so gravity without matter. And indeed, you find that solutions can exist when you relax that. So there was a recent paper, Marolf and Santos, that discussed several different setups like that.
All right. So you say that even in the context, let's say, of n equal 4 super-Young meals, you may have something like this.
Yeah.
Okay.
And actually, there's a related wormhole that we'll discuss even for n equals 4 super-Young meals that doesn't even have any funny sources turned on. So.
All right. I'm looking forward to that.
Yeah, so it really is a puzzle. The thing that you would have liked to be true is you say, okay, let's study a particular theory where there's no, which we think is dual to a special theory, like n equals 4 super-Young meals. And then we just find magically that there's just no wormholes. That would have been a lovely conclusion to this. For that theory, you just don't have any wormhole solutions, and it's consistent with factorization. That does not seem to be the case. That's not what happens. These wormholes still can exist, and we have to understand why, how they're compatible with the factorization of the boundary theory. So how can we resolve this tension? I'm not claiming that this implies that ADS-CFT is incorrect. I think what it implies is that we need to understand the bulk theory a little better, understand what else there is besides the wormholes that can restore the factorization and can solve this problem. Okay. So those are the three puzzles associated to wormholes. So there was this, is coherence lost? And our tentative conclusion there is that no, it's not. The state remains pure, but there's something else funny that's going on. Then there's this non-locality, and the interpretation of that is that it's not really non-local, it's just an average. It's an ensemble average over theories. And that's also, yeah. Then the third puzzle is, okay, fine, suppose it's an ensemble average. How can that possibly be consistent with ADS-CFT? And that's a big puzzle. That third one is a major puzzle that is not resolved, and it's an active topic of research. And the answer is not going to be that ADS-CFT is wrong. It's going to be that we have to understand the bulk theory a little better. That's my opinion. Okay. Oh, sorry. Another answer that you could have given, and this is, I think, the answer that many people would have given a few years ago, is that you would say something like, okay, the wormhole solutions exist, but they're not on the integration contour. Like, we're just not supposed to include them. Like, the bulk theory says, just don't include the wormholes. You can write down solutions, but just don't include them. And I think that's not the right answer either, because in some cases, those wormholes that look puzzling actually give you the right answer to some quantities. So we'll discuss that later. So I don't think that you should just throw out the wormholes or assume that they're not on the integration contour. But I also don't think it means ADS-CFT is wrong. There's some kind of middle path where we have to understand some additional effects in it on top of the wormholes. Okay.
By the way, since you've just mentioned this, we had invited Renate Loll a few weeks ago, so one of the specialists of discretized approach to path integrals. And okay, her point of view was that you should not include the wormholes. Maybe we convinced her that probably you should include them. But okay, there was a discussion. But now I have a question related to this. What can we say about the old-fashioned 2D quantum gravity in the light of these new developments? Because in the old days, people claim that they had managed to find some non-perturbative, at least some non-perturbative information about 2D quantum gravity. You had all these nice Pain-Levé equations and with all these double scaling limits, blah, blah, blah. It was not fully non-perturbative, really, because as you know, right? I mean, these nonlinear equations, the solutions depend on parameters, etc. But still, it seems that they had, we had there some rather deep understanding of quantum gravity in 2 dimensions. Do you know if the recent insights, shed a new light on those old things, or?
Yeah, the new light that they shed on that is that we can sort of think about those correspondences in the context of ADS-CFT, more like we think about it using the perspective of ADS-CFT. So when this work was done, people mainly thought about that 2-dimensional theory as being like the worldsheet theory, the string worldsheet theory. And now we like to think about that as being like the space-time. So now we think about this correspondence between those 2-dimensional quantum gravity theories and the matrix integrals as being a kind of ADS-CFT correspondence,
right, where
the matrix integral, the matrix of the matrix integral, is a Hamiltonian of a quantum system. And there you see explicitly that the full theory, it's an average. You're integrating over Hamiltonians. You're integrating over matrices. So in that case, the duality is between a quantum gravity theory and an average over quantum systems, an integral over quantum systems. So it's kind of like the Coleman story.
I see.
So that's an example where it kind of works. You include the wormholes, and it really describes an ensemble average in the boundary theory. But I think there are other examples, like n equals 4 super Mills, where that's not the case, where there's no ensemble average, and the bulk theory has to be different. It has to work in a different way than for those for the theories that you mentioned.
Okay, we'd have to talk more, but okay, let's keep going, because it would bring us too far away, I think, from the.
Well,
that's interesting.
Maybe we can return to it. I think it's an important question. So, okay, so let me just review some. Finally, we'll write some equations, not too many, just a little. We want to start to investigate whether there are solutions like this. So we've discussed some of the conceptual puzzles associated to them. Now we want to see, are there solutions of this type? So let's imagine that we have a metric that looks like this. And let's work with a negative cosmological constant, because we have an eye towards ADS-CFT applications. So we'll assume a metric like this just for simplicity, and we can write a differential equation for A. So this is a Friedman equation. This is like the 0,0 component of Einstein's equations minus rho matter plus 1 over the ADS scale squared. I'm setting G Newton equal to 1 plus K over A squared. So this is the curvature. Okay, so this is the Friedman equation that determined that this A of tau has to satisfy. So tau is a Euclidean time direction. And oh yeah, one important thing here is that this rho matter, this is the rho matter, like the G0 component in Lorentzian signature for tau. So you should think about it as being positive, being the physical sign, most easily physical sign of rho m. Okay, so our goal is to find a solution that looks something like this, where A goes to infinity over here, A goes to infinity over there, and it has some minimum value somewhere in between, and somewhere we know that A dot has to equal 0, because it's very big on one side, very big on the other side, small in between. It has to have some minimum value somewhere. Okay, and let's just think about this equation at the point where A dot equals 0. So first, let's say rho matter equals 0. So let's consider a vacuum solution. And let's assume the curvature is positive. So this is the setup for the theorem that was proved by Witten and Yao. And basically, they proved that in this case, there are no wormhole solutions. And of course, they didn't do it by studying this simple Friedman equation. They did it in general, but we can see the consequences of their theorem even in this simplified setting. So if we set rho mat equals 0 and we have k positive, then you can see that the right-hand side of this equation is going to be positive. So it's impossible to solve the equation a dot equals 0. So we can't have a wormhole solution. But suppose k, okay, so that's one important result. You don't have a wormhole solution in just pure gravity if you have positive curvature on the boundaries. And we can see an example of that here. But what if we take the curvature to be negative? So if we take k to be negative, then you can have solutions. This argument doesn't forbid it. And in fact, a of tau is equal to cosh of tau will be a solution if sigma is just a quotient of hyperbolic space. So that's just another way of writing a quotient of the vacuum ADS solution. So this is a solution, a of tau equals cosh tau, and some negatively curved space. So we can imagine here some kind of some space with negative curvature, which gets big on one side, small in the middle, and big on the other side, and that's a perfectly legal solution. Okay, another thing we can do is we can have rho m bigger than 0. And if rho m is bigger than 0, then even if k is 0, or even if k is positive, then we could imagine solving this equation, a dot equals 0. And basically, this is how the examples of Madison and Maus and Arkani-Hamed, Orger, and Polchinski work. And it was recently discussed in a nice paper by Marolf and Santos. They go through a whole bunch of examples where they get some positive rho m and find wormhole solutions. Okay, so the wormhole solutions do exist, but not in the kind of simplest case. So there's something a little bit hard about constructing them. You can't have them in the simplest case where we have a positive curvature boundary and vacuum Einstein's equations. So there's some obstacle to constructing the wormhole solutions, but it isn't fatal, and they do exist. So I wonder, maybe instead of continuing here, maybe I should stop at this point and see if we can have some discussion or take questions. And next time we will kind of start from this point again, go through some of these considerations in more detail in JT gravity, and see if we can find applications for these wormholes. I could go on now, but it's been, well, an hour and 40 minutes. You guys are probably tired. I'm just warming up because it's morning here, and so our comparative advantage is shifting. But I don't want to tire you folks out.
So, questions? And please don't be shy. There has to be a lot of questions. There were a lot of non-trivial things that were said conceptually. So I'm sure people have a lot of questions. Well, Douglas, maybe it was too clear.
I doubt very much that's the case. No,
Try
it's just
to be a bit less clear next time.
I mean, I've been there. It's hard to. It's you know, it's weird, right? It's a little hard to ask questions. Feel comfortable asking questions over Zoom, but.
So if really there's no question, I mean, maybe you keep going for 10 more minutes, and then at the beginning of next time we'll try to have questions.
Okay, yeah, we can do that. We can do that, sure.
So let me ask again to people. So still no question at this point?
Well, I have one, if I may.
Sure.
Could you please go to the third point when you have first two conclusions on the purity and on the inequality in the gravity? So yes, this one's. What does it mean? I know it's a very general question, but does it mean that the baby universe has no impact on the general universe, but its gravity is different than the general universe? Or what is the general conclusion here?
Okay, the conclusion. So first of all, this is a great question. Thank you. But the conclusion is supposed to be that the baby universe represents the random couplings that we're integrating over. So there's some average. This theory really is described by some average over couplings, this alpha. And the baby universe represents the value of alpha, basically. So if we think about, let's forget about exactly how that works for a second and just explore whether that can explain these funny results that we found. So then we interpret G as being an average over alpha. So we think of G as a function being average over some couplings alpha. And let's just think about that. So trace of rho is some observable. The average of trace of rho squared does not have to be the square of the average of that thing. So if we're averaging over some parameters alpha, then this top equation with question marks looks okay. At least looks mathematically possible, right? So the average of the square doesn't have to be the square of the average. So that seems okay. And then the conclusion is just that since the effect of the baby universe is just to implement this average over alpha, then what we have here is really just an average of pure states. And since each realization, each value of alpha corresponds to a pure state of the universe, then when we average that, so when we compute G in the bottom line here, when we compute G of the left side or the right-hand side, they're equal realization by realization, value of alpha by value of alpha. So averaging over alpha, the equation remains true. It's because basically this thing is linear. This equation is linear in G, and the top equation is nonlinear in G. So that's supposed to be the lesson we're supposed to take from this, that the state of the universe is pure, but it depends on this thing alpha that we're averaging over. And the effect of the wormholes is to describe that averaging. Now, maybe I can try to make the connection to why the wormholes and alpha are related. What you're supposed to do is you're supposed to think about a wormhole. So we have some wormhole like this. Think about it in the following way. I don't know if this cartoon is going to be helpful. Think about that thing as representing a projector onto some state alpha. And so we can think about that as like the wormhole caps off somehow with some boundary condition alpha here, and caps off in the other direction with some boundary condition alpha here. So then we think about the wormholes being replaced by some kind of a projector onto alpha, state alpha from the left and state alpha from the right. And the connected wormhole is what you get when you average over the coupling alpha. And if you have different copies of this alpha variable, then when you average over it with a Gaussian weighting, they can connect up in any pattern, any way they like, in any pattern of Wick contractions. So if we have 4 of these things, and we think about each of those things as being projections onto alpha, and then we integrate over alpha, then we can connect them like this. That's one possible Wick pairing of those objects. Another possible Wick pairing would be this. So the calculus of wormholes, of connecting these things together with wormholes, corresponds to the calculus of Wick pairings, which is like the calculus of an average of some variable over a Gaussian measure. So that's supposed to explain why the wormhole and the average over alphas are related to each other. I'm not sure if that's so you asked a question, what does it mean? I don't know if that was in the right direction, but if you want to ask again, I'm happy to try again.
It's not easy to grasp it, you know?
Yeah. Yeah, it's not easy. Now for me, a very helpful thing was this equation here. So this equation here. So to me, the top line looks intuitively like the effect of a wormhole, because it allows this bilocal coupling, this bilocal interaction between very distant points. So that looks to me like it describes, so let's take our space-time, and that describes some kind of annihilation of a particle at x and creation of it at y. And that's exactly what can happen if you have a wormhole that's linking those 2 points. So the top line describes, in effective field theory language, the effect of a wormhole. You have non-local coupling between these 2 points. And the bottom line is explaining that effect, that non-local effect, is really just the same thing as an average over some coupling, some local coupling, alpha. So this was really helpful for me in understanding, making sense of the connection between wormholes equals average over couplings.
I agree this is very intuitive, but it's not clear if this is quantitative, you know, versus qualitative. Qualitatively, it's a very nice and very clear picture, I agree. Whereas this is enough to really, you know, because I don't think we really know how to compute rigorously the effective action associated with the wormhole contribution. So whether, you know, this picture is really valid at a fundamental level, that's still quite non-trivial. I mean, right? That's not clear. That's non-trivial. Do you?
Yes,
right?
That's right. That's right.
It's very well attractive, but
right. But so for a real wormhole of some finite size, it's more complicated than just this interaction. But I think all that we're really assuming here is that it can be kind of expanded in some terms in the low energy effective theory. You can expand the effect of the wormhole mouth in a sum over operators in that theory. And so instead of just operator phi, we should have a sum over operators and a sum over corresponding couplings. And if we just use the approximation where the wormholes are, okay, that's one step closer, one step towards the real situation, towards, but it's actually, it's not fully satisfactory, because that picture does not take into account the mapping class group redundancy in different ways of describing the wormholes attaching to the same space. So that picture is not entirely satisfactory, as you said. And a more satisfactory answer, in my opinion, is, you know, simple models where you can actually compute the wormholes and show that they do lead to the effects of an ensemble of a particular type. So this picture is not, yeah, exactly what you said. This picture is suggestive and kind of guides our thinking, but then in actually trying to study these things quantitatively, we have to write down a particular theory, analyze the wormholes, see what the answer is, and see if indeed the answer is an ensemble average of some kind.
So your understanding, because you mentioned that, I'm sure you're going to come back in the following lectures, but since we have 5 minutes left, so let me ask. So your feeling is that in a genuine quantum gravity, like realistic guy, these effects will have to be sort of canceled out by other subtle contributions, right? That's what you say. You still believe that quantum gravity is really quantum theory.
Well, yes, I do. And there's an asterisk there, which is that I think it can go both ways. So there are well-defined quantum gravity theories that are truly dual to an ensemble of quantum systems. So that is a possibility. But it seems like that might be a rather special case that has to do with these low-dimensional kind of stupid theories of gravity, like JT gravity, dilaton gravity, maybe three-dimensional gravity, or these kind of Chern-Simons theories. For a more interesting gravity theory, we don't know what the generic case is, whether it's dual to an ensemble or not an ensemble. I don't know how to answer that, but we do have very good evidence that there are at least some special theories of gravity that are dual to specific quantum systems. And that might be the generic case in higher dimensions because it's hard to come up with ensembles of quantum systems. So yes, there's very strong evidence that there are theories of gravity that are dual to specific quantum systems. And those theories of gravity can include wormholes. So based on that evidence alone, I would be led to believe that there must be some other contributions that can cancel the wormholes. And okay, it just so happens that those specific theories of gravity have a whole bunch of stuff in them that we're not describing with just these wormholes. They have strings and branes, and there's a lot of complicated bulk physics. And it seems like there's room for magical effects to happen within that complication. Magical effects that can cancel the wormholes in some way and restore factorization. And I think that must be what happens. And I don't know how to prove it or how explicitly we'll ever be able to show it. But I hope we'll get closer.
Is there strong evidence that the progress recovering the page curve, I mean, I guess I'm jumping ahead now, applies equally well to these theories where you expect a single theory, okay, or could it be an artifact of these low dimensional models which which correspond to ensembles?
Good, yeah, wonderful. Okay, good. So let me try to amplify your question a little bit because I think it's a really important one. So there are these one application of wormholes is to explain the page curve of a black hole. And so you say, okay, if wormholes are supposed to be a property of an ensemble theories, and if they get canceled out in theories that are not dual to an ensemble, does that mean that the wormholes that describe the page curve also get canceled out? And I think, okay, now let me try to answer the question. I think the wormholes will only cancel out in quantities where they need to cancel out. So the cancellation will be very delicate. And so in a quantity that's supposed to factorize, like this quantity here, something must cancel the wormholes. But for the page curve computation, nothing needs to cancel the wormholes. There's no factorization puzzle for the page curve. And I think in that case, the additional effects that we include, the strings and branes and whatever, must make a very small correction to the wormhole answer. Another way of seeing that is that if we compute the page curve in an ensemble of theories, then the actual answer is very close to the ensemble average. So it's what's called self-averaging. And I think basically the most likely scenario is that wormholes just don't cancel out for self-averaging quantities. And so in that case, I would say that the wormhole probably is a correct explanation or correct first term in a computation of the page curve, but it remains to be shown. There's actually in the third lecture, we can discuss an example where you can show that. It's unfortunately not an example in n=4 super Yang-Mills, and it's not even an example of entropy or anything. It's a very stupid finite dimensional integral example inspired by the SYK model. But the one advantage it has is you can see exactly this happen. You can see that the wormhole cancels out when it needs to, And in computations where it doesn't need to cancel out, it does not.
Okay, great.
Excellent. So do we have one more question?
I might have a question. So when you were computing those traces of rho and with the squares, if I understood correctly, the presence of this baby universe part was part of the definition of the state rho. Is that correct?
Yeah, yes, that's right.
So how are we supposed to understand this? What did you do to this state so that there would be like a baby universe attached to it?
Good. So what I did is I imagined that the fact that a baby universe was recently formed is something that the observer can tell. They don't know exactly in what state the baby universe was formed, but they know that it was formed. I'm borrowing some intuition from the evaporating black hole, where you can tell that a black hole, it makes sense to kind of restrict to the subspace of the full Hilbert space, where some black hole was recently formed and evaporated. And I'm assuming that something like that restriction also makes sense in the context of the baby universe. That it makes sense to restrict to a subspace of the Hilbert space where that happened. That may be a good approximation for some kinds of baby universes and a bad approximation for other kinds. In particular, it's probably only a good approximation for a fairly large baby universe, which really isn't so different from a black hole. So the idea is that the observer in the regular universe is going about their daily life, and they're like, whoa, there's some weird gravitational waves or some kind of pattern in the geometry, and they say, aha, this is a strong indication that a baby universe was just born. And conditioning on that, they then compute the entropy of the final state of all the matter. It's possible that there's some important subtlety there that I'm overlooking, but it certainly makes sense in the context of an evaporating black hole. And that was part of my motivation in explaining this setup, is that basically the same thing happens there.
So you're assuming some information loss that happened due to some quantum fluctuation or something like this, or?
Well, yeah. So I'm not sure if you mean the quantum fluctuation corresponds to the creation of the baby universe. Is that what you meant by
yeah, I'm just trying to understand how it just happens like this without anyone trying to make this baby universe happen.
Well, that's how tunneling happens. That's how these effects happen, even in quantum field theory. Like, nobody is trying to make it happen. It just has some small probability of happening at any time, and eventually it happens somewhere. That this instanton process takes place. So yeah, it's some large quantum fluctuation. It's very rare. It has exponentially small probability, but it can happen, and we can condition on that having just happened.
Okay.
Like saying, I want to study the properties of this particle, conditioning on the fact that it just tunneled out of this false minimum in the potential in quantum mechanics.
Okay, thanks.
All right. So probably it's reasonable to stop now. So Douglas can go and have his breakfast, probably.
Yeah. Thanks, you guys, for staying around. And next time we'll discuss some applications of these wormholes in JT gravity. And the final time we'll discuss a little bit a theory where you can see how the wormholes get canceled by some other contribution. Okay.
So we meet on Friday at 4 p.m. Brussels time. Same time, exactly the same as today. Okay.
Okay, sounds good. Yeah. See you guys.
Thanks a lot, Douglas.